Hello everyone, good afternoon. Let's start today's class. As we had thought and planned, we finished the last chapter, that is acoustics of small rooms, etc., in the last class. Today we will talk about noise. So we are getting into the last section of our syllabi where two chapters of noise are left. Ideally, I should have covered all the three chapters of noise because noise is such an important issue in our life. Nevertheless, we will cover the two. I recommend all of you to read the third chapter on your own. The first chapter, 31st, talks about the various sources of noise, how you can identify them. The second chapter talks about the impact of noise on humans. And the last chapter talks about how to reduce the noise. So that's how the three chapters are planned. They are very important for us. We'll cover two of them in the classroom. Okay, let's go ahead. So we will talk about the noise in the environment, different sources of noise levels, how do we evaluate, calculate the noise levels. We'll talk a bit about outdoor noise. So let's go ahead. What are the different of sources of noise? So you know that a noise is basically defined an unwanted audio signal. So there is no particularly harsh rules about noise. What could be music to one person may be noise to other person. So if the sound is unwanted, it becomes noise. And by that token, every source of sound is also a source of noise as well. Here we will list some of them that we use in our day-to-day lives. So vibrating solid bodies, bars, membrane, plate, loudspeaker cones, etc. Loudspeaker cones are obvious. But look at your home. I mean, at your home, you will find many of these examples if you observe carefully. If you close the door of your home, then the door panels will hit the frame and they get set into vibrations, creating noise. In fact, if people have the habit of closing the door harshly, it will bang on it every time. Then bars and membrane utensils in the kitchen. Remember, if you are using utensils in the kitchen, they occasionally hit each other and create noisy sound. So these are all the sources of noise at home. Vibrating air columns, musical instruments as we are familiar with. Bottle, if you blow through the bottles, then it may create some sort of source of noise. If you have a hollow chamber, hollow rooms, and the wind is blowing across, then still wind can vibrate, giving some type of sound. Flow noise in the fluid due to turbulence or leaking air. So, a lot of examples of this at home. For example, our fan, ceiling fan. Fans are the classic sources of noise at home. So they are they are moving, they are the moving blades through which the air is flowing, and that interaction produces a lot of noise. In fact, if you increase the speed, the noise increases. We will talk more on the flow noise in the next class. Air conditioning noise can happen. Air conditioner can give noise both ways due to vibrations and due to the flow of air. Interaction of moving solid with fluid, that is another case. Like wind blowing itself gives noise or it's noisy. But along with that, when it hits, say, some metal part, some solid part, then that interaction also produces noise. So even that is a noisy thing. So, interaction of solid with fluid. Similarly, water. You open the water tap, you will hear some sound. The water hits the bucket, you will hear another sound. As long as that flow continues, the air column vibrates, the bucket plastic may vibrate. There are going to be sound for from everything. Rapid changes in temperature and pressure. So normally it may not happen at home, but some examples are still there. Example, the whistle of a pressure cooker. Suddenly it whistles, it's a rapid expansion of air, hot air. Remember that. Same way, if it's outdoor and if it's lightning, or maybe some chemical explosion, some bomb, Diwali cracker. All these are the example of sources of noise where there are rapid change in temperature and pressure. And the shock waves. Shock waves are generally not experienced in urban phenomena because they are created by the sources of sound which are moving with the speeds greater than that of sound. So many of the jet planes and all have the capacity to move at a speed greater than the speed of sound, but generally in urban areas they don't operate, so we don't experience them. Also in rural areas they operate at much high altitude, so the sound becomes feeble. But yeah, they are the sources of noise, particularly for the people who are operating them. So one has to be careful. Now, how much part of mechanical power is converted into sound power? So you know that our world is particularly noisy place now. I'm using the word now because most of our sources of noise, if you look around, be it vehicles, be it airplanes, trains, cars, fans, air conditioners, etc., etc., etc. Most of these sources of noise are created in last 100, maybe 150 years or so, or maybe 200 years. Faraday discovered Faraday's law of EMI around 1821, 1822. We are in 2021, 22. So around 200 years. And most of these noisy development has occurred now. For millions of years, human beings were living in a very quiet environment otherwise. So, how much mechanical power is converted into sound power? One would realize that it's very little. Very little energy, very little mechanical energy is converted into sound. Here is a graph that gives us the relation between mechanical energy and the sound energy. I'll come to it in a while. If you use A level meters, A weighted sound power meters, we have already talked about them much earlier, and plot these graphs, you will get the how much fraction of mechanical energy is converted into sound energy. I've enlarged the graph so that it is visible on a small screen as well. And you will find that it's a very interesting graph. And we have to use this graph in the problem solving in the exam, etc. So we need to learn how to use it. So you can see that an automobile, which is a classic source of noise, it uses around 10 power 4 watt of mechanical power. How much sound does it convert? How much of its energy it converts into sound? What fraction? You can see it's 10 power minus 2. So there's an order difference of 10 power 6. That means its mechanical power output is 10 power 6 times larger than its sound power output. Sound power output is 10 power 6 times smaller than the mechanical power output. Same is true for other things also. Turboprops, airplane, jet planes, etc. They produce anywhere 10 power 7 watt. The noise is just 10 power 2 or 10 power 3 watt. So very small part we have to remember of the total energy is converted into sound energy. Now how do you measure the noise level? So noise levels are measured in a very straightforward way. You just use your A level meters. Mostly A level meters are used, which suppresses low frequencies. We have seen those scales A, B, C. So A level meters are normally used for measuring noise. In a free field, doubling distance drops noise level by 6 dB. So we are familiar with that. Now, in if you have to measure day-to-day life noise, say the noise on a street, then you need to take some sort of averaging process, because noise may not be constant at all the time. Even on the Diwali day, when people are bursting crackers, sometimes noise can be more and sometimes noise can be less. So your meter reading will fluctuate. So we need to make an average of those readings. So an averaging procedure is generally carried out. One of the averaging procedure represents the noise level in LX scale, where what it means is the level exceeded X% of the time. That means if it says level exceeded 10%, suppose L10, so level exceeded 10% of the time. So you have to decide a threshold first. Say this is my threshold, and now of the total time of observation, let's say total time of observation is 1 minute, then I would say that for 10% of the time the noise was more than the threshold. So that is a very important criteria here. So another way to average it out is energy equivalent. It is defined as the decibel level of the steady noise that would give the same total energy over the same time period. So steady noise you take, you find a steady noise equivalent. For example, 100 dB noise short. It's a short noise, very powerful. 100 dB is very powerful. If you're standing close, hear it for long, or even if you hear it for a short time, it may cause damage. 100 dB lasting for 3.6 seconds is equivalent to 70 dB noise, which is also fairly uncomfortable. 70 dB noise lasting for 1 hour. So that is the equivalent, energy equivalent. So noise, large noise, if it is for a small time, we use the energy equivalent or L equivalent method. The other option is L day night. L day night is added to the nighttime readings. Normally, same level of sound appears more annoying in the night time. Suppose normal afternoon conversation happening at 60 dB will not be very noisy. It will be just loud. But nighttime the same conversation would sound much noisy, and therefore in the nighttime sensitivity, uh, keeping in mind of the nighttime sensitivity, all the noise levels are rated by adding 10 dB to them. So here is a summary of what we have just discussed. You can have a straightaway reading, A level sound pressure level, then L10 reading, which figures out that of the total time of observation, when the noise level exceeded a threshold by 10% of the time. L50 means the noise level exceeded the threshold for the 50% of the time. Similarly, L90, L equivalent we have seen is used for noise which occurs for a very short distance of short time interval. And there are others also which we are not discussing, PNL and EPNL, perceived noise level, effective perceived noise level. Now, outdoor noise level or noise is very, noise has particular characteristics. If you are staying in a tall building, you may feel that at a higher level, since you are away from the source of noise, which could be on the ground, say a loudspeaker playing, then you might be insulated from the sound. A present day in Mumbai, there are metro railway tracks are being laid through the very densely populated areas. So people living at the higher floor may feel that since they are away from the metro, it will not affect them. But that is not correct. The noise in a free field spreads out in all possible direction, but if the noise is happening on the ground, then the type of ground cover does affect the spread of noise. So if the ground is not plastered, if it is earthy, if it is a mound, grassy cover, etc., etc., then in that case it will absorb a lot of sounds. A lot of sound is absorbed by soft ground. Forest, even better. If you have a tree cover in front of your home, that will absorb lot of sound. So most of the time highway authorities, if you have seen, particularly little outside from the city limits, you will notice that on both sides they plant trees that will insulate the buildings behind automatically by from noise. At a higher altitude, refraction takes place. Remember, what happens is as the altitude increases, the temperature also increases because sun rays, depending upon again the time of the days. So, I mean, if you are not at the early morning or a clear night, this is typically the gradient. So at higher here, if you are here at a higher temperature, you are having a higher altitude. And as you come towards the ground, the temperature decreases. And therefore, as the in the daytime, as the atmosphere becomes little rarer, the sound will travel away, refraction will happen. Early morning, the ground cools down, and then there are some fluctuation in this gradient, and accordingly, the sound energy can be diffracted in different directions. Clear night, the fluctuation is of different type, and this fluctuation can also change. So remember, depending upon what time of the day the noise is being created, you will get a refraction effect. However, you will notice that in all the three, although in this case it is strong and in this case it is weak, suppose if there is a tall building and if you are playing a loudspeaker in front of it, the upper floor people are more likely to get strongly affected than the lower floor people. Sound waves are indeed very mildly, weakly absorbed by the atmosphere. So, as the distance from the source increases, you will find that the sound intensity drops. Now, the ground affects in very interesting ways. We have seen that if it is mild, grassy surface, it absorbs quite a bit. But there is a trouble. I'll come to it. Certain frequencies can absorb by grounds more strongly than certain other frequencies. So you will get some dips or holes in the spectrum. For example, if it's an aircraft noise, then typically the ground absorbs at around 250 hertz and 800 hertz, and therefore you get dips there. So that is one that leaves gap in the spectrum. So people sitting at distance may not get the entire spectrum of sound to hear. Then hard ground is a good reflector. So if it's a concrete surface, and here is the source. It will send, direct sound will travel, reflected sound will travel. Both the sounds will have some phase difference because their paths are different, and therefore an interference will take place over here, and that can give distortion to the sound which is being heard at this point. If it's a soft surface, as I said, then it tends to absorb the sound energy. But in that process of absorption does not happen at one place. Sound keeps progressing forward as, or sound waves, longitudinal waves keep progressing forward as they get absorbed in the sound. That results in a third type of wave which is called as the ground wave. So that ground waves, the impact of ground wave is that the sound may reach to even to the shadow region. So if there are some buildings or some places which are in the sound shadow, the sound can travel along the grounds and reach to those places too. Now we will take specific cases of noise. Today we are going to talk about machine noise. So machines are important. Remember that machines that you will experience in day-to-day life, fan is a machine. If the fans are not working properly, then they make a lot of noise. The mixer grinder at home is a machine. Again, if there something is unfit over there, then it may create a problem. If you have been to a flour mill, atta chakki, what you call it, then you know that it's a machine. Again, an example. An exhaust fan is also a machine. Washing machine, of course, is a machine. So there are a number of appliances, instruments in the home and surrounding us which are machines. So large number of machines will convert only a small fraction of their energy into sound, not the large fraction. Now what makes noise is all the rotating parts like gears, frictions, fan. If there's an impact, you know, for example, if one part hitting the other one, turbulence. Turbulence is again as usual if there are moving fluid, magnetic hum, etc. Then all these we are going to create machine noise. So normally we try to reduce the source noise in various ways, decoupling the source from the resonator. So one of the key things that happen is that your machine could be making some noise, but maybe on the table on which it is operating, the table starts vibrating, and therefore that creates some more, even more noise. That's a resonator. Similarly, a typical example is a window air conditioner. You fix it in the window. As it operates, you may find that the entire window sets into oscillation. That is quite possible. So normally we decouple the source from the resonator. So typically what happens in a split AC, that you decouple the moving parts from the non-moving parts, damping the resonator. So damping can be put like in an air conditioners, ideally when they are used, when they are installed, typically rubber paddings must be used so that the machine damping happens and machine noise is not created. Balancing rotating parts. If the rotating parts are out of balance, out of gear, then again it may create noise. So you need to balance it. It happens in cars, vehicles, when the wheels are a little bit out of balance. Rotating fans also. We use accelerometers as well in order to figure out if there are accelerated parts, how much noise are they making, and greasing, applying grease at different parts so that the noise reduces. Typically, if there are sheets, metal sheets, rectangular metal sheets of length L, height H, and width W, then their frequency of oscillations are given by this formula, where H is the thickness, LW is width and length and width, and M and N are integers. So this is the formula which will give you different frequencies of oscillations of a solid pan. Okay. So yeah. So that's all about today's class. We talked about different sources of noise, and in particular, we talked about how to measure the noise. And in particular, we talked about the machine noise. In the next class, we are going to take up flow noise and some other example of noises, and then take up some problem to wind it up. Thank you.